a problem. Who would like to do that? I know I would, because there's no way to jog your memory like doing a practice problem. It says here in this pop-up question, how many lone pairs are in, it should say how many lone pairs are on the central atom. How many lone pairs are on the central atom in SEBR3 minus? Now I'm going to walk through this one with you. We're going to do the whole thing together. And before we get into this one, I want to remind you of a rule that we looked at probably towards the end of the last lecture. And that was that if you have an element, a central atom, okay, that is an element that comes from the third period or beyond, it can expand an octet. That means it can be surrounded by more than 8 electrons. And in fact, we're going to see that occurring in this very example. Now, first, let's start by tallying up the total number of electrons. Selenium is in group 6A. Okay, it's a group 6A element. That means it has 6 valence electrons. Bromine is a group 7A element. It's got 7 valence electrons, but there's 3 bromines. Now remember, because we have a minus charge, we have to add 1 electron. So that means we're going to add 1. So we've got 21 plus 6 is 27 plus 1 is 28 total electrons. Now, since we have SEBR3, right, there's 3 bromines, that tells us that our selenium is going to be in the center and that the bromines will be on the periphery. Let's start with that. So we're going to draw our selenium. We'll draw 3 bonds and we'll put 1 bromine on the end of all of those. Now, usually, not always, there are exceptions, but usually when you have iodine, bromine, or chlorine, those atoms will almost always have 1 bond and 3 lone pairs. Almost always. Are there exceptions? Yes, but very. I told you that fluorine always has 1 bond and 3 lone pairs. No exception, okay? But these other 3, iodine, bromine, and chlorine, usually have 1 bond and 3 lone pairs. And so we could start putting some electrons on those bromines. And then once I've done that, we're going to do 2 things. We're going to tally up the total number of electrons that have been used first. Okay, let's just stop and do that. Can anybody tell me, out of my total of 28 electrons, in this structure that I've got drawn so far, how many electrons have I used up? Nothing more than that. Yeah, I see that my students are answering 24, and they are exactly correct. If you're unsure of where the students got that number from, let's just run over it. Remember, a bond represents 2 electrons. So we have 2, okay, let me just delete that red, okay, so we've got, let's count it. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used up a total of 24 electrons so far in this Lewis structure. Now, if I take 28 and I subtract 24 electrons, that means we've got 4 electrons left over. Before, and I know that most of you know what the answer is, but before we solve it, finally, I have one more question for you. Do the bromine atoms in this Lewis structure, so far, what I've drawn, do they have an octet? Yes or no? Do they have an octet? Okay, great. I see my students saying yes. Now, if you're unsure of what I mean by that, remember that bromine is in group 7A. It wants to take on 1 more electron to be isoelectronic with, with krypton. So if we look at the total number of electrons, bromine is 1, 2, 3, 4, 5, 6, 7, 8. Because remember, the 2 electrons in the bond are shared. It's a covalent bond. So that tells us that each one of the bromine atoms in what we've drawn so far, they all have an octet. Okay. Another question. I know I'm going kind of slow, but this is important. Does the selenium have an octet? Yes or no? Okay, I got my students here, Liv, Joel, Isabel, the whole gang. They're all saying no. That's right. The selenium does not have an octet. Now remember, selenium is found in period 4. Okay, so let's write that out here. Selenium is in period 4 and can expand its octet. Okay. So that means that the last 4 electrons that we have, we're going to put them on the selenium. 1, 2, 3, 4, like that. Okay, so that's my Lewis structure, and the number of lone pairs in my selenium is 2. Okay, And if you're thinking, you know, I need even more practice on this, I practiced it all weekend, started on Friday, didn't stop until Sunday night, woke up at 4 a.m. this morning, started all over again, but I need more practice. Well, here we go. Let's try another practice problem. It says writing Lewis structures for molecules with single bonds and more than one central atom. Now, it says the problem is write the Lewis structure for methanol. It gives us the molecular formula, an important industrial alcohol that can be used as a gasoline alternative in cars. I wouldn't recommend it because methanol burns with a colorless flame, and so there's some inherent dangers there. But I digress. Let's get started on this question. If you're the kind of person that enjoys puzzles, just literally solving puzzles, like maybe Sudoku or I don't know, any kind of puzzles, then Lewis structures might be for you, okay? Because there's a little bit of a puzzle here, but how do you solve a puzzle? You use the clues and then you piece it all together. The first thing I want to ask my students is, can anybody tell me how many total valence electrons there are in CH4O in this molecular formula? Total valence electrons. Somebody said 14. Anybody else have an idea? Somebody says 12. Somebody else says 14. Okay, let's tally them all up. Well, carbon has 4 valence electrons, and hydrogen has 1 valence electron, but there are 4 hydrogens, and oxygen is in group 6A, so it has a total of 6 valence electrons. We tally all that up, we get a total of 14 valence electrons. Now, remember, hydrogen, right, H can only have 1 bond. Right? Hydrogen can never have more than 1 bond. So that tells us that we're going to have both carbons and the oxygen, both the carbon and the oxygen attached to each other. Okay. Now, if you're wondering now, how did you know that, Mr. Dion? How do you know that the carbon and the oxygen have to be attached to each other? Because there's a couple more things that I used here at my disposal. Carbon always has 4 bonds, okay, and no lone pairs, and oxygen has 2 bonds and 2 lone pairs. And if you're wondering now, where did you get that, Mr. Dion? I got it from last class. Okay, and so with that in mind, that means that we could draw 1, 2, 3, 4 bonds to our carbon and 1 bond to our oxygen like this. Okay, now we can place the hydrogens around 1, 2, 3, 4. If we tally up all the electrons that have been used, 1, 2, 3, 4, 6, 8, 10. We've used up 10. 14 minus 10, subtract 10, electron gives us 4 electrons. Can anybody tell me where these last 2 electrons should go? They're going to go on the oxygen. Why? Because oxygen always has 2 bonds and 2 lone pairs. Now, I should say there's exceptions to this. It's when an oxygen is uncharged. But anyhow, we're going to put the 2 lone pairs like this. Now, that's the answer. Okay, that is the final answer. Now, if you're wondering, hey, Mr. Dion, you solved that kind of quick. You know, I don't know if I would have put that together that quickly. Well, without me sounding like a meanie, you kind of should be able to put that together that quick. And if you're being like, okay, Mr. Dion, you're being a jerk, hold on. Remember, if you were to try to do something like this, that's a big no-no. Okay, that's impossible. It cannot happen. If you were to try to put, you know, 2 hydrogens together like this, and then that's impossible because a hydrogen cannot have 2 bonds. You see, you got 2 bonds to a hydrogen. So literally, the only possibility, and you can take this to the bank, is that the carbon and the oxygen have to be attached to each other in order for us to have all of these 4 hydrogens on the periphery. Okay, I also employ these rules. So that's why it's wise to know those rules. If you don't know where they are, if we back up here in our notes a little bit, where was it? Let me go back. Back it up, back it up, back it up. Here it is. In nearly all their compounds, carbon forms 4 bonds. Oxygen has 2 bonds and 2 lone pairs. I gave you a couple of examples. So if you need to go back to the previous lecture and review those, by all means, do that. Where's my problem? Here it is, right here. Okay? And so that's how we solve the Lewis structure for methanol, just like that. Let me ask you a question. Does the carbon have an octet? The answer is yes, it does. If you're unsure, let me prove it to you. Look, 1, 2, 3, 4, 5, 6, 7, 8. There we go. The carbon has an octet. Does the oxygen have an octet? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Do the hydrogens all have a duet? Yes, they all have one bond, which results in a duet. And there we have it, folks. That's our Lewis structure for methanol or methyl alcohol. Let's move on from there and talk about Lewis structures for molecules that have multiple bonds. So that means a double or a triple bond. If there are not enough electrons for the central atom to attain an octet, then you've got to have a multiple bond. Then you're going to move on to the next step, which is if the central atom doesn't have a full octet, change a lone pair on a surrounding atom into another to the central atom, thus forming a multiple bond. The good news for our class is that we already looked at the structure of CO2 earlier on, which had a double bond in it. And so let's give these two a try. The solution's okay, I have two problems here. Let's start with A, which is ethylene. It's important, an important reactant in the manufacture of polymers. It's also important as a ripener for fruits. Ripen fruit. Let's see here, C2H4. Let's do it slowly. Could anybody tell me how many total valence electrons are there in C2H4? Not a trick question. This would be on doth not like it, the trick question. Okay. Yes, good. All my students are saying 12 valence electrons. If you're unsure, carbon has 4. There's 2 carbons. Hydrogen has 1. There's 4 hydrogens. That's 8 plus 4 gives you 12. So we've got a total of 12 electrons. Now, I'm going to go over this a little bit quickly, but remember, hydrogen can only ever have one bond. And so we could think about having our 2 carbons bound together like this, maybe having 1, 2, 3, like that, and then 1 hydrogen over here. But then how many electrons have we used up? We've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that means we've only got 2 electrons left. And this carbon does not have an octet. So let's put those 2 electrons there. Could anybody tell me what the problem is with this Lewis structure that I've drawn? And there is a problem with it. Can anybody tell me what the problem is here? Major problem. Carbon needs to, okay, good. 2 things. I like what 2 of my students said. One person says carbon needs to have 4 bonds. This carbon does not have 4 bonds, so that's an issue. And then somebody else said the carbon on the right doesn't have an octet, and you're absolutely right. Look, this carbon only has 1, 2, 3, 4, 5, 6. This carbon has an octet, but the carbon on the right doesn't. And so we're going to have to rethink our strategy here. So let's delete those 2. What if I was to make it symmetrical in that I put another hydrogen over here like this? Now I've still got 2 electrons to use up. Now, if I were to put them here on this carbon, now this carbon has an octet, but this carbon doesn't have an octet. So hopefully you're seeing what I'm getting at, is that the only solution is for those 2 carbons to share this lone pair of electrons. How would they share them? They're going to share them in, starts with C, ends with covalent bond. That's right, bond between the 2 carbons, like this. Okay. Now, do the 2 carbons, do they both have an octet? Yes. 1, 2, 3, 4, 5, 6, 7, 8. Good. 1, 2, 3, 4, 5, 6, 7, 8. Also good. Okay, so both of those carbons have a complete octet. Let me just show you. And so this is a perfectly legitimate Lewis structure. I would give, if you wrote that down, I give that 100%. Let me just show you one more thing to think about as we move forward. Electrons are negative, right? They have a negative charge. There's 2 electrons in here, 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 2 electrons in here. If we have like charges, do like charges attract one another or do they repel each other? Like charges.
Repel.
Absolutely. Couldn't agree more. And so what bonds want to do, and we're going to see this even more, especially in section 10.2, is that there's nothing. So look, I want you to hear me out here clearly. There's nothing wrong with this Lewis structure. I'll give that 100%. But as we get better and better at our Lewis structures, you're going to realize that that's not probably the best way to represent it. You would want to draw the Lewis structure like this. And if you're saying like, why would you want to do that, Mr. Dion? Because what you want to do is you want to try to maximize the distance between all of those shared electrons. You want to get them. You ever heard the expression "quit crowding me, bro"? They want to quit crowding each other, right? Get out of my face, okay? Electrons, I can relate to them. They just want to be free. Has anybody ever heard the expression "don't fence me in"? You know, they just want to have wide open spaces like the Dixie Chicks, okay? They just want to have room. Is anybody else like me? Wants to have room? And yeah, maybe I'm the only guy. Maybe everybody who's listening to me is an urbanite. I don't know. But anyhow, I like to have space, right? I like to have some nice open space. And so the electrons, they want to get away from each other as much as possible. So they try to maximize the distance in between them. And that is what we're going to really look at in dirty detail when we cover valence shell electron pair repulsion theory. And if you're thinking, you know, Mr. Dion, you're getting ahead, I just want to put that bug in your ear before we get there. Well, let's try one more. Let's draw the Lewis structure of nitrogen. I'll go over it quickly. Nitrogen is in group 5A. It's got 5 valence electrons. We get 2 of them. That equals a total of 10 electrons. Now, if you start doing something like this, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a big problem here with this Lewis structure that I've drawn. Neither of these nitrogens have an octet. Now, you're probably thinking, okay, I'll just take one of those like that. Chocolate. Now you can see that this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It's got an octet. It's perfect. We'll hold the phone there. This nitrogen does not have an octet. 1, 2, 3, 4, 5, 6. We have Houston. We have a problem. Okay, so let's delete all that spinach that's on there, and let's erase the lone pair over here, and we're going to share 2 more electrons like that. Now that is a perfectly legitimate Lewis structure. Again, I like to maximize the distance between all of my electrons. So I'm going to move these over to the side to make it prettier. But now you can see that both of the nitrogens have a full octet. 1, 2, 3, 4, 5, 6, 7, 8. They both have a complete octet. But now we've got a triple bond in our nitrogen. Give me a thumbs up if you followed me on the formation of this Lewis structure for N2, nitrogen gas. Cha? I used to say that. I know I told you this, but last spring I used to say that to my students all the time, and they would be like, "Cha, Mr. Dion, cha." Okay, good Canadian humor there. Okay, well, with that in mind, let's give another one. The old college try. One that I have here. 10.3. Do you guys have that in your notes? Question 10.3. Pop-up question 10.3. You guys have this one? I think I put it in the notes. Yeah. Let's give this one a shot. Okay, 10.3. I'm going to give you a second just to try and draw the Lewis structure of SF2. Don't Google it. Okay, you could go. Don't Google it. See if you can draw it. I'll give you a minute to think about it. I'll take another sip of coffee. Is there a way, you guys are more tech savvy than me, is there a way that my students, meaning you guys, would be able to take a picture of, you know, a proposed Lewis structure that you're drawing and put it in the chat, or would that take too long to upload it? Like, would you have to take it with your iPhone and then, you know, post? Is there a fast way to do it? I don't think there is. I've seen students post things that they've drawn before. You can screenshot your screen. Okay. You can share your screen. Zipping, snipping, told, I don't know, drawn MS Paint. Anyhow, I'm not sure how to do it. Like, I see that Isabel is loading something. Oh, yeah, okay. All right. So, Isabel, I'm not sure how you did that, but I like it. Okay. So, how about this then? If you're able to do it, I'm not going to force you to do anything here. This is the land of the free. But if you're able to just share a screenshot like Isabel did, and if you could just, you know, snip tool, paste, shove it in there and just show us a structure that you propose. If you want to do that, I really enjoy looking at the students propose. whether it's right or whether it's wrong, this is the place to learn. Okay? So if I ever ask a question about a structure and you want to paste it in, by all means, you do that. Nothing would make this guy happier. Okay, let's who was it that posted it? Isabel Davis. I like that, Isabel. It looks pretty reasonable to me. Let's see how Isabel got there. Look, sulfur is in group 6A. It's got a total of 6 valence electrons. Fluorine is in group 7A. It's got a total of 7 valence electrons, but there's 2 fluorines. So that's 14 plus 6 equals 20 valence electrons. Now, sulfur is less electronegative than fluorine, and so sulfur is going to be our central atom. Remember the rule about fluorine? Fluorine always has 1 bond and 3 lone pairs. Now the 2 fluorines have a full octet. How many electrons have we used up thus far? We've only used up 16. 2, 4, 6, 8. Who do we appreciate? 16. Okay, we've used up 16 total valence electrons. If I take 20 and I subtract 16, that means I've got 4 electrons left over. The sulfur does not have a complete octet. In fact, it's 4 electrons shy of an octet. So that tells you that the lone pairs are going to go in the sulfur like that. Now the sulfur has an octet, the fluorines have an octet, and my Lewis structure is perfect. Okay, there's nothing wrong with this Lewis structure. And so there are 0 double bonds present in sulfur difluoride. Give me a thumbs up even if you didn't get it right, if you follow me on the rationale. Just follow me on the rationale. Excuse me. Let's see. Okay, good. Got a bunch of people giving me a thumbs up. All right. There we go. Sulfur difluoride Lewis structure. Who's enjoying Lewis structures? Anybody? Just me? I think some of my students like Lewis structures. Very handy. Also, for anybody who's interested in taking organic chemistry at UCCS or anywhere else, Lewis structures are going to be very, very important for organic chemistry. So important that eventually you'll be able to draw them. I'm not kidding. Pretty much in your sleep. You know, we draw so many Lewis structures in organic chemistry. All right, good one, Aurora. They're great, right? Now let's talk about another Lewis structure here, and that's the Lewis structure of O3, which is ozone. You've all heard of the ozone layer. So ozone, if you draw the Lewis structure, in fact, it can be drawn 2 different ways that are exemplified by 1 and 2. Now the book goes into a little more detail about this, but I'm just going to boil it down to the necessary items for chemistry 1401. If you look at any one of the oxygens in either of these structures, look at this oxygen here. Okay, it's got 1, 2, 3, 4, 5, 6, 7, 8. Perfect. It's got an octet. Look at the central oxygens in both of them. 1, 2, 3, 4, 5, 6, 7, 8. That's got an octet. Good. Look at this oxygen over here. You know, 1, 2, 3, 4, 5, 6, 7, 8. Every oxygen in both of these structures has an octet. Now you might be thinking, come on, Mr. Dion, these are the exact same thing. All I would have to do is draw an axis like this and spin this around 180 degrees, and I'd end up with this. So they're identical. They're not different. You're crazy. Well, hold on. They are different. Okay? If I number the oxygens 1, 2, and 3, and I number these 1, 2, and 3 like that, and I say the numbers, represent the actual oxygen atoms, then you see clearly that these are 2 different Lewis structures. But they're both reasonable. In fact, they're both correct, right? Now, here's the interesting part. If you've never heard of resonance structures before, this is the crux of what this section is about. It says neither structure depicts ozone accurately because in reality, the oxygen bonds, the oxygen-oxygen bonds, check this out, have the same length and have the same bond energy. What? What? How can that be? Hold on. Hold the phone. Look. You look at this structure, you say, hey, there's a double bond, Mr. Dion, and there's a single bond. There's a single bond, there's a double bond. What you need to understand is that if you were to shrink yourself down to the atomic level, you're not going to actually see the letter O anywhere, okay? You're not going to see a stick. You're not, right? A Lewis structure is just a way for us to represent a molecule. And in reality, the bond length in ozone, both of these bonds have the exact same length. What does that tell you? it tells you that neither one of these is a single bond and neither one of these is a double bond. Hold on. What are you talking about? Well, it's not really a double bond and it's not really a single bond. In fact, it's a hybrid in between the two. And that's what resonance structures are. Let's take a look. It says here the structure of ozone is actually shown more correctly using both Lewis structures, and we call those resonance structures. A two-headed resonance arrow is placed between them. This is a resonance arrow. Okay? If you have these arrows like this is an equilibrium arrow. So don't get the two mixed up. They don't mean the same thing. Resonance and equilibrium are two different things. So we draw the two resonance structures of ozone. We place that resonance arrow in between them. And what that tells us is that these are both representations of the ozone molecule. And they show what's called the delocalization of electrons. If you look down here, it says resonance structures have the same relative placement of atoms, but different locations of bonding in lone electron pairs. That's what I call delocalization, because the electrons are not in one locale or one place. They are throughout the molecule. Now, I don't want you to think, oh, they're vibrating. You know, 1 minute these electrons are here, then they move over here. No. It's not switching between back and forth. In fact, there's no one Lewis structure that could completely accurately represent the structure of ozone. Okay, the actual structure of ozone is a hybrid of these two. All right. Somebody says, why don't we just use curved lines? I mean, we use a circle for benzene rings. It seems the same principle idea. Well, we can use a circle inside a benzene ring, which represents delocalization. But if you want to be accurate in drawing what's called a mechanism in organic chemistry, we don't draw a benzene with just a circle in the middle. Okay, there's a lot of limitations there, actually. We usually draw benzene like this. In fact, when I teach organic chemistry, I very rarely draw benzene with a circle in the middle. I almost always draw it this way. So again, there's some limitations with that. Now, what you're asking, Jonah, is, couldn't we draw, something in between these? Yes, you can. You can draw what's called a resonance hybrid. So a resonance hybrid. And we're going to look at that in a couple of slides. So let's keep moving and talking more about our ozone molecule and explaining what a resonance hybrid is before we look at it. It says the species, like ozone, which can be depicted by more than one valid Lewis structure, is best represented by a resonance hybrid. Resonance forms are not real bonding depictions. So both of those structures, those resonance structures that we drew of ozone, neither of them, okay, fully represent the ozone molecule, because the ozone is not vibrating. It's not switching back and forth between those two resonance forms. The real structure is the resonance hybrid, which again, we're going to look at on the next slide. Now, before we do that, here's the analogy that's used in our textbook. I actually put the picture in here because I thought it was so funny. And she said, well, if you make a burro or a mule, if anybody here has ever, bred a horse and a donkey, you know that what you get. Has anybody ever heard of seedless fruit? If you make, you cross a monocot and a dicot in biology, and you can make seedless fruit. That's how they make seedless oranges and seedless grapes. Well, if you cross a horse and a donkey, they can mate and they can produce an offspring, but that offspring is unable to produce offspring. So a mule is a seedless fruit, right? They can't mate with another mule. But anyhow, if you think about what a mule is, when you look at a mule, it's not a horse 1 second and then a donkey the next second, right? It's not a horse and it's not a donkey. It's a hybrid, right? It's something in between a horse and a donkey. The other analogy that she uses, I'm giggling just thinking about these, is she said, well, what if you have the color purple? The color purple is a mixture of blue and red. If you have a purple mule, you don't look at it in 1 second, it's red, and the next second it's blue. No, it's always purple. So that's what she means by a hybrid. Now, Jonah, this is what I'm getting at. Resonance hybrid that's drawn right here. It says Lewis structures depict the electrons as localized on either an individual atom or as a bond in between two atoms. But in a resonance hybrid, the electrons are delocalized. Their density is spread over a few adjacent. So the dotted lines are used to show the delocalized electrons. So instead of, I'll just draw one of the resonance structures, which looks like this, okay? What they do is they say, well, since this bond, right, these two electrons are shared here and here, they kind of remove that bond. Let me show you. You delete that, and then you say those two electrons are shared like that by that dotted line, okay? That's a resonance hybrid. I don't want to get myself painted into a corner here, but I don't think I asked. I'd really have to look, and you'll have to challenge me on this because I haven't looked at your next midterm or exam in a long time. I wrote it a while ago. I wrote it in the summer, and so I don't remember if I asked questions about the resonance hybrid, but I know that in organic chemistry, what I always tell those students is you need to understand the resonance hybrid. Okay, I'm not going to ask you to write me a 3-page essay on resonance hybrids, but you still have to understand it. Okay, now I want to switch gears just for a second and talk about, the types of bonds in this resonance structure, because if we go back to, one of those resonance structures, and I told you, okay, well, the bond lengths are the same, right? This bond length is the same as this bond length. And then you're probably thinking, okay, well, what is it? Are these bonds double bonds or are they single bonds? And in fact, they have what are called fractional bond orders. Here, if you just looked at that, you might think that's got a bond order of 2. This has a bond order of 1. And what we're going to see is that's not actually the case. And there's an easy way for us to figure that out. It says that resonance structures have what are called fractional bond orders. And the way that we calculate that is we divide the number of electron pairs between the number of bonded atom pairs. How many electron pairs do we have? Maybe I should start it with the denominator first. How many bonded atom pairs do we have? We have a pair of bonded atoms here, and we have a pair of atoms there. So that's 2 bonded atom pairs. Okay, so that's that part. The numerator says the number of electron pairs. That means the number of shared electron pairs. Maybe I could even write that in there to help you out. We'll put in here shared, like that. How many total are there? There are 1, right? Each bond has a pair. So there's 3 divided by 2. That gives you 3 over 2. Okay, that equals 3 over 2, or 4, 1 and 1/2. So the bond order here, ready, mind blown. The bond order for both of these, BO, is equal to 1 1/2. Like what? Half a bond? Yeah, that's the bond order. Okay. Hold on, my computer's doing something funny. Give me 2 shakes of a lamp tail. Come on, please don't die on me now. Not a good time. Darn it. Sorry, the screen of my Mac just went totally black and it won't. Here we go. Come on. Sorry about that. I'm just waiting for my computer to. There we go. Getting some more beach ball love here. Okay. A long question here. Let's start with this question first, okay? And then we'll back up. There we go. Okay, let's try this question, and then we'll come back to pop-up question 10.4. I think this question is a lower in order of magnitude of difficulty. What does it say here? Write resonance structures for the nitrate ion and find the bond order. Okay, so let's just start by drawing the Lewis structure. I think I gave myself space here to solve this Lewis structure. If you're the kind of person that's feeling, rusty or, finding these challenging, remember, don't just watch me do it. Give it the old college try. I'm going to give you guys a second. It's hard for Mr. Dion to be quiet in class. But I'm going to give you 20 seconds to look at this, see if you can come up with at least a plan, the number of valence electrons. All right. I see that somebody typed in the number of valence electrons, and that person is correct. So nitrogen is in group 5A. It's got 5 valence electrons. Oxygen is in group 6A. It's got 6, but there's 3. And then we add 1 for the negative charge. And so that's 18 plus 6, which gives us 24 valence electrons. Okay. Let's see, what else? We're going to have our nitrogen in the center. We're going to have, let me maybe put this off to the side and move my slide up here a little bit. Okay, so nitrogen is going to be in the center. It's the less electronegative element. We're going to put 3 bonds to oxygen like this. So we've used up 6 electrons. We got 1, 2, so let's see, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24. There we go, done. There's a major problem with this Lewis structure. Can anybody tell me what the major problem is with this Lewis structure? There's something really out of whack here. Thank you, Amanda. Good. The nitrogen doesn't have an octet. So let's rectify that first. And in order to do that, we'll just move one of the lone pairs from the oxygen over here like this. Now, nitrogen is in period 2. Nitrogen cannot exceed an octet. Okay, so we've got that much done thus far. The next thing I want to do is I want to calculate the formal charges. You guys remember the formula for formal charge? Is it right? Formal charge is equal to, the way we calculated was the valence electrons. Valence electrons subtract sticks, subtract dots. Okay, let me just fix this here. There we go. Formal charge. And when you do that, you find that the formal charge on these 2 oxygens is -1. The formal charge on the nitrogen is +1. And the formal charge on this oxygen is 0. Right? How did I do that? Let's just do the oxygen as a practice. Okay, the nitrogen has 5 valence electrons, subtract 4 sticks and 0 dots equals +1. Like that. So that's the charge on our nitrogen. Now, it says here in the question, what they're asking us to do is to draw all of the resonance structures. Let's do that. We're going to draw a resonance arrow. We're not going to draw a curved arrow showing the movement of the electrons, but you can see that we've got 2 single bonds and a double bond, right? Or at least that's what it looks like in this resonance structure. And so that double bond could be on this oxygen I have highlighted in yellow, or it could be on this oxygen that I have highlighted in green. So let's draw the other resonance structures. So we're going to start by drawing our single bonds to oxygen like this. Remember, the double bond could be here or it could be here. Then we're just going to fill in the valence electrons like this. That. Come on. So then we'll have a positive charge on the nitrogen no matter what. We get a negative charge here and here, here and here. And there we go. Those are the 3 resonance structures. Now, let's think about our bond order. Our bond order. Okay. Let's go back to the formula to make sure that we know what the formula is for bond order. It was the number of electron pairs divided by the number of bonded atom pairs. Well, let's go. Oops, I didn't mean to do that. Let's go back here. The number of electron pairs that's being shared is 4, right? We have 1, 2, 3, 4. So we'll put that in. 4 divided by the number of pairs of atoms, or bonding pairs. How many bonding pairs do we have? We have 1, 2, 3. So 4 divided by 3, sorry. There we go. 4 over 3 is equal to 1 1/3. So it's like each one of these bonds isn't a single bond, it isn't a double bond. It's like 1 1/3 bonds, like that. That's our bond order. Capiche, caposh? Did anybody follow me on that one? Bond order? Sure. Hope so. All right, one person. I'll take it. Take that to the bank. Good, great. Tanner, Megan, Don, group. Okay. Here's the solution. Now, good news is I've already taught you a formal charge. In fact, we went over it last lecture. We've gone over it today. So you know how to calculate formal charge. And I told you that this is the Dr. Diaz version. I'm not going to take the credit for it, the old fixed minus dots, but hey, it works really, really well. Here's the formula that's put forth in our book, which is just, so she subtracts number of unshared valence electrons, so that's the dots, and 1/2 of the shared, so that's 1/2 of the bond, so that means the number of sticks. Either way works. I find the sticks and the dots things is easier for students to memorize, so I'll keep working with that. What are the formal charges in this ozone? Let's do it together. So what's the formal charge on this A? Well, oxygen has 6 valence electrons. Subtract 4 dots and 2 sticks equals 0. So no charge here. What about this oxygen in the middle? Oxygen has 6 valence electrons. Subtract 3 sticks and 2 dots equals +1. So that means there's a +1 charge on that oxygen. What about this oxygen here? This oxygen has 6 valence electrons. Subtract 6 dots and 1 stick equals -1. So that tells you this oxygen has a -1 charge. Look, you got +1 and -1, and they balance out, right? O3 does not have a charge, okay? Ozone is just O3. There was no charge, okay? And so they balance out like that. If you want to calculate the formal charges in the second resonance structure, number 2, you'll see that they're -1 and +1. Don't believe me? Give it a try, okay? Don't try this at home. I say do try this at home, okay? Make sure that you're able to calculate formal. What I was just saying is that the formal charges have to add up to the actual charge on the species. So if you look at, again, the formal charges on A, B, or C in either structure number 1 or 2 of the 2 resonance forms of ozone, you end up with a sum of what? 0 each time, right? You tally up 0 plus 1 and -1, you get 0. You tally up -1 plus 1 and 0, you get 0. Look, let's go back to our nitrate example. Look, we had the charge on nitrate is only -1. If you take -1 plus -1 plus +1, what does that give you? -1. Right? It should work out. So one of the things I enjoy about Lewis structures is that there's a lot of self-checking you can do. The formal charges should add up to the overall charge. You can always check for octets. As long as you know the rules, you can really, check and double check and recheck everything in Lewis structures. All right. Well, with that in mind, I'm getting a little ahead of myself with this next slide. This slide kind of bleeds into the next section of the chapter, which we're not into yet, but I guess it just shows you formal charges on boron, carbon, nitrogen, and oxygen, which are very common elements that we study in general chemistry and organic chemistry. These come up all the time. Let me give you a pointer here, and this applies to everybody. I don't want you to think, oh, Mr. Dion's talking about organic chemistry. Let me just zone out. I don't need to know that. I just use it as an example because I teach a lot of it. But if you were to study organic chemistry, you would have all of these literalized, within the first couple of weeks because you see them so many times. You'd say, well, if I have nitrogen with 4 bonds, it's going to have a +1 charge. If I have oxygen with 3 bonds and a lone pair, it's going to have a +1 charge. If I have carbon with only 3 bonds, it's going to have a +1 charge, so on and so forth, right? If I have a nitrogen with 2 bonds, 2 lone pairs, maybe you can't see my circle, that's got a -1 charge, right? Now, if you're thinking, well, Mr. Dion, this isn't organic chemistry, I don't need to know that. Yes, you do, because you need to understand why each one of these central atoms in the top row has a charge of -1. We need to understand why each one of these central atoms in this row has a charge of 0, and why each one of these central atoms in the third row all has a charge of +1. And the more Lewis structures that you practice, the more you'll be able to just look at it and say, okay, well, this nitrogen has, 3 bonds, 1 lone pair, it's neutral. this oxygen has 3 bonds and 1 lone pair, it's got a +1, so on and so forth. It's really important that you're able to do that. Okay? Well, with that in mind, let's talk about resonance structures a little bit more. Again, if you are interested, and I think many people who are taking this class are interested in taking General Chemistry 2, Organic Chemistry, anybody who's interested in medicine or a career in medical school or dental school, of course, you have to take Gen Chem 1, Gen Chem 2, Organic Chemistry, if you want to do biochemistry, biology, all those things. And so choosing a more important resonance form is important in just about any undergraduate, chemistry class that you're going to take in Gen Chem or Organic Chemistry. Anyhow, it says here that how do we choose the more important resonance form, right? If we have more than one resonance form, is one preferred over the other? And the answer is, in the resonance structures that we've looked at so far, no, but in some cases, yes. And of course, we're going to look at those kind of examples right now. So here are the rules, is that smaller formal charges, whether they be positive or negative, are preferable to larger ones. And so if you can have a resonance structure, let's say, where you have, let's say a plus, let's say you could have, a +1 charge, a +1 charge and a -1 charge, something like that. That would be preferred, right? Because overall that has a charge of +1, then having a +2 and a -1, right? We just always prefer to have smaller charges. That's just one, quick example off the top of my head. Sign doesn't look very pretty there, does it? Like that. What else? The same non-zero formal charges on adjacent atoms are not preferred. So an example of that would be if you were to have something like this, a carbon with 3 bonds and then an oxygen with 3 bonds and a lone pair, then you'd have 2 positive charges. You're never going to see the same charge on 2 adjacent atoms in a Lewis structure. That's a big no-no. What else? A more negative formal charge should reside on a more electronegative atom. That's most of the time. There are some exceptions to that rule, but yeah, usually we try to put the negative charge on the more electronegative atom. Let's see here, what else? So let's take a look at NCO, which is the cyanate ion. So cyanate, write that in here, cyanate, if you want, some students like to Google everything, and there's no problem with that. Now, if we were to spend some time drawing the resonance forms or the resonance structures of cyanate, which is a polyatomic ion, we would come up with these 3 structures that are shown here. Okay, we'd come up with 1, 2, and 3, and then we would go about assigning the formal charges. Keep in mind that the cyanate has a -1 charge overall, and if you evaluate these 3 resonance structures, one of them is going to be preferable to the other 2. And in fact, that is this one here, okay? This is going to be the preferred resonance form. All right, now how did I arrive at that decision? Well, let's take a look at it. It says here that resonance forms with smaller formal charges are preferred. If you look at the first one, we have a -2, right? So that's not going to be an important contributor because the other ones only have -1 in them, right? We wanted to get rid of any, or sorry, not get rid of, but any resonance structure that has higher charges are not going to be preferred to those with lower charges. So that's the first rule, okay? But then it becomes a battle between 2 and 3. How do I decide between those 2? Well, if you look at the second bullet point, it says a negative formal charge should be placed on a more electronegative atom. So resonance form 3 is preferred to 2. The negative charge in 2 is on nitrogen. The electronegativity of nitrogen is 3. It has an electronegativity of 3. The electronegativity of oxygen is 3.5. And so that negative charge is going to preferentially be on that more electronegative element. Now, overall, the overall structure of the ion is a weighted average of all 3 forms. But forms 2 and 3 are going to contribute more than 1, and form 3 is going to contribute more than 2. Now, if you're wondering, what's the take-home message from this, Mr. Dillon? What do I have to be able to do here? You would have to be able to evaluate from a series of resonance structures which one would be the preferred contributor. All right. So that means you would have to assign, or you would have to be able to utilize these rules that we've just covered. Well, by this point, you might be asking, what's the difference between formal charge and oxidation number? Because we spent some time calculating oxidation numbers, and we spent some time calculating formal charges. Well, there's a big difference between the two, because although both are simply methods of electron bookkeeping, okay, again, if you were to shrink yourself down to the atomic level, and this is just, I just circled the central, the middle one is an example. You're not going to see the letter N. You're not going to see dots. You're not going to see sticks. You're not going to see the number -1, -3, right? These are just things that human beings have come up with to help us explain molecules, ions, atoms, right? These are just ways that we come up with for explaining different phenomena. And so formal charge and oxidation number both have their place, but they are different ways of electron bookkeeping. For formal charge, bonding electrons are shared equally by the atoms. Now, the formal charge was that formula: the valence electron subtract sticks, subtract dots. The formal charge is going to change, or can change, sorry, I should say, the formal charge of an atom may change or can change between resonance forms. Let's look at an example. The formal charges are the ones that are in yellow. Look at the formal charge of the nitrogen. It goes from being -2 to -1 to 0, depending on the resonance form you're looking at. Okay, well, what about oxidation number? Oxidation number, for an oxidation number, bonding electrons are transferred to the more electronegative atom to get a full octet on every atom. The oxidation number doesn't change throughout the resonance form. Again, let's look at nitrogen. With our oxidation numbers, it doesn't change. It's always going to be -3 each time. Now, just to review how to calculate the oxidation numbers, I'm not going to go over formal charges because we just did that. But where did that -3 come from, for example? Let's just do the first one. Well, in oxidation number, we assume that the electrons are transferred to the more electronegative atom. What's more electronegative between carbon and nitrogen? The answer is nitrogen. That means that nitrogen is going to take those 2 electrons as if it was its own. That means that the oxidation number is going to be 5 valence electrons, subtract 1, 2, 3, 4, 5, 6, 7, 8. 5 subtract 8 gives you -3. What about the carbon? The carbon has a single bond here and a triple bond here, but they're 2 nitrogen and oxygen. Both nitrogen and oxygen are more electronegative than carbon. Therefore, the carbon has, it's as if it has no electrons. 4 minus 0 gives you 4, right? Plus 4. Same exercise with the oxygen. It's as if the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. 6 valence electrons, subtract 8 gives you -2. Okay? And so that's where we get those oxidation numbers. Again, oxidation number will not change throughout all of these different resonance contributors. Okay? All right, so you have to know the difference between oxidation number and formal charge. All righty. There we go. Look, here's kind of a summary. If you're, just angry at oxidation numbers and you're angry at formal charge, here's an explanation, okay? Here's something to ease the pain, okay? Neither an atom's formal charge or oxidation number represents an actual charge on the atom. Okay, but both of these types of numbers simply serve as different methods to keep track of the number of electrons. They both have their place. Absolutely, they both have their place in chemistry. And you have to be able to use either one. Now, if you're getting scared and saying, well, do I have to know when to do which one? Not really, I wouldn't say in this class, okay? If I ask you a question where you need to address formal charge or oxidation number, it's usually something that will become abundantly clear to you, all right? So it's not about me trying to trick you or make something so confusing that you can't figure it out. No, no, no. Well, as one of my students so aptly put it a number of semesters ago, a real funny guy, he had a, this guy would always get us laughing in class and always had the fun expressions that he would come up with. One of them was, and I probably told you this 100 times already, but he said chemistry is nothing more than learning a bunch of rules and then the exceptions to all those rules. So let's take a look at some exceptions to the octet rule. We've already looked at one of them a few times, and if you're wondering what is that, that was the expanded octet, when we have a central atom that comes in the third period or below, so third, fourth, fifth, so on and so forth. That's one exception. Another one is molecules with electron deficient atoms. And boron and beryllium are the two atoms that you need to be aware of, that they are commonly electron deficient. In fact, beryllium usually just forms two bonds. Okay, so beryllium forms, beryllium forms two bonds for Be, and boron forms three bonds. Three bonds for boron. In the book, she goes into a little bit more detail, but I'll be frank with you, you don't need to know anything more than what I just wrote in black ink, okay? Two bonds for beryllium, three bonds for boron. What about an odd electron species? You probably noticed that everything that we've dealt with up until now had an even number of electrons. But if you have an odd number of electrons, like let's say you have NO2, if you have NO2, you've got 5 times 2 plus, did I put N2O? Jeepers, Mr. Dion. I was like, that doesn't work. NO2, you got nitrous oxide on the brain. Anyhow, not really, not literally, okay? Good chemistry joke there, anyhow. 5 plus 6 times 2. That gives us a total of 17 valence electrons, so that's an odd number. And when we have an unpaired electron, a single unpaired electron, we call that a free radical. As you can see, we have an unpaired electron on the nitrogen or the oxygen here. We'll talk more about free radicals before the next exam or midterm. The expanded valence shell, I went over this with you. So phosphorus, see here, phosphorus and sulfur are both in the third period, and so they can expand their valence shells. All right, and the reason they can do that is because they have available d orbitals to put those extra electrons into. Sorry, just shuffling through my notes here. Well, with all that in mind, let's do some problems. All right, it's 10:28. We got lots of time. Let's try some good problems. Who's ready? Who is ready to try some good practice problems? Chemistry class. All right, so if you don't have a pencil and paper, go grab one, Go grab one from a friend or maybe your own. But anyhow, let's get started. We'll start with A, which is xenon tetrafluoride. So XeF4 is the xenon tetrafluoride. Hey, I'll just throw it out there to my students. Can anybody tell me how many valence electrons total would there be in XeF4, xenon tetrafluoride? Anyone? Sorry, maybe I need to scroll down here in my chat. Oh, yeah. Sorry. There we go. Somebody says 36. Somebody else says 36, I think. Somebody else says, we're getting a lot of 36s. So that's probably right. Let's take a look. Xenon is in group 8A, right? Xenon is a noble gas. And so xenon has 8 valence electrons. Fluorine is in group 7A. It has 7 valence electrons. There's 4. So that's 7 times 4, which is 28. 28 plus 8 gives you 36 valence electrons. Okay. Well, we know that fluorine only ever has one bond and 3 lone pairs, so we can just, knock this out pretty quickly. We got the xenon with 1, 2, 3, 4 bonds to fluorine. You have to fill up the octets on all of the fluorines. That's a rule. For that rule. So now I've used up 8 times 4, which is a total of 32 electrons. 36, subtract 32 electrons, and we carry the 6, Anyhow, that gives us 4 electrons left over. Not a trick question. I'll ask my students, where are those Where are those 4 electrons going to go? Mr. Dion does not like trick questions. That's right. Absolutely, Alexis. They go on the xenon. Yes. 1, 2, 3, 4. Now let's count up the number of electrons on the fluorines. 1, 2, 3, 4, 5, 6, 7. That's an octet. All 4 of the fluorines have an octet. Let's look at xenon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, remember, xenon is past the 2nd period. Xenon is in the 5th period. Right here, Xe, xenon is in 5th period. And so it can expand its octet. It can go past an octet of electrons. All right. Let me do you one better. Let's calculate the formal charge on the xenon. Xenon is a noble gas. It's got 8 valence electrons. Subtract 4 sticks, 4 dots, 0. Pretty cool, huh? Who thinks Lewis structures are kind of neat? I do. I really do think Lewis structures are pretty neat. Okay. You don't have to answer that. Let's see. You know what? Let me just stop for a second here. Are there any questions? Any like burning questions that anybody has about anything to do with class, Lewis structures? Because we're going to try the next one in a second. No? Is anybody there? Double checking my chat. Curious why those 4 electrons aren't split. I'm not sure what you mean by split, because electrons are paired in orbitals, right? Every orbital can hold 2 electrons. Those 4 electrons aren't split. Well, there's no way that you could draw a resonance contributor for xenon tetrafluoride, right? There's no possible resonance contributor here because the fluorines all have a complete octet. Do non-preferred resonance forms occur more rarely or never? No, remember, it's not occurring, Blake. And I'm not trying to be a jerk, okay? I just want to help you out with the wording, okay? It's not occurring. Remember, if you draw any of those resonance forms, none of them accurately represent what's going on. Blake, if you really want to get into some dirty detail on this, you can look up what's called an electrostatic potential map. In an electrostatic potential map, they use color coding to show you where more of the electron density is. Maybe you could look up a couple of those just for fun, and it might help you understand, that it doesn't mean that it doesn't occur, okay? Because none of the resonance forms occur. It's just it's just helping us understand where more of the electron density will be if you have unequal sharing, okay? So ozone isn't a good example because that's symmetrical. But in the cyanate ion, if you look at an electrostatic potential map, you'll see that more of the electron density will be towards the oxygen. Does that help a little bit? Does that help you understand a tiny bit? Okay, you nodded. No. There's nothing wrong with asking a question in this class. What's another question? The resonance structures are only if there's a double or triple bond, right? Yes, usually we have to have not. I'm trying to think here. I don't want to misspeak. Usually it's when we have a double or a triple bond. Yeah. In fact, I think she even makes that blanket statement in the textbook. Okay. I hope that clears up some misconceptions or some questions that you might have. Let's give the next one a try. H3PO4. That's phosphoric acid, right? I asked you to memorize that acid. Was anybody able to calculate all the valence electrons in H3PO4? How many total there are? We got 3 plus 5 plus 24. Sorry, I'm slow in my math today. That gives us what? 8 plus 24? That gives us 32. 32 valence electrons. All right, there we go. Okay, well with this one, this is one of those ones that might be a little more T&E, a little more trial and error. There's nothing wrong with trial and error. I have no issues with trial and error. But remember, phosphorus is the only element here that is in the third period or beyond, right? It's in the third period. So that means it can expand its octet. Right? So if we draw our phosphorus and we put all the oxygens on that like this, and if you're wondering, okay, how did you get that far already, Mr. Dion? Well, remember, hydrogen can only have one bond. Okay, so hydrogen has to be bound something like this. Now, how many electrons have we used up thus far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 32 minus 14, that means we've got a long ways to go. But remember, oxygen always has 2 bonds in 2 lone pairs when it's uncharged. Okay, so if I have 2 bonds on these oxygens and I put 2 lone pairs, then I've used up a total of 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3, 24, 25, 26. When I say subtract 26, then I've got a total of 6 electrons left over. Well, where can those electrons go? Remember, the oxygen always has to have 2 bonds in 2 lone pairs if it's uncharged. If I put 2 lone pairs of this oxygen and make a double bond to the phosphorus, now I've used up all of the electrons, and all 4 of those oxygens have 2 bonds in 2 lone pairs. Yes, some of them have 2 single bonds, and one of them has a double bond, but it still represents 2 bonds in 2 lone pairs for each one of those oxygen. Each hydrogen has 1 bond, and the phosphorus has an expanded octet, right? Because it is in the third period. It can do that. So expanded octet. Don't believe me that it works out? Let's calculate the formal charge on the phosphorus. Phosphorus has 5 valence electrons, subtract 5 sticks and 0 dots, gives you a charge of 0. And that's the Lewis structure of phosphoric acid. All right. The problem with the structure that I'm seeing here, Isabel, is that oxygen can never have 4 bonds. Okay, one of your oxygens has 4 bonds to it. So oxygen can never have more than 3 bonds in a lone pair. Also, I think you might have vastly exceeded the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons around the phosphorus. Like that. Okay? So not only have you exceeded the octet rule for the phosphorus, it would also have a formal charge on it, right? Because it shouldn't have a formal charge even though it exceeds the octet rule. All right? Let's take a look at, do I have room on here? Hey, I do. Let's do BFCl2 is the last one. Let's calculate the total number of valence electrons. Boron has 3, fluorine has 7, chlorine has 7. There's 2 of those. That's 21 plus 3. That's a total of 24 valence electrons. What was the rule for boron? Don't believe me? Let's back it up. We said that boron, okay, is commonly electron deficient. Not always, but commonly. Boron commonly forms 3 bonds. And with that in mind, let's go here. Let's draw a boron. Oh, is it getting late? Oops. Boron, we'll draw 1, 2, 3 bonds to it like this. Fluorine always has 1 bond and 3 lone pairs. Chlorine almost always has 1 bond and 3 lone pairs. Look, boron has 3 valence electrons. 3 minus 3 sticks and 0 dots is 0. Everything's perfect. So the rule that's being broken here is boron is electron deficient. Okay, it can have 3 bonds.